Okay, for week 7, there's quite a bit of stuff to get through, and it kind of depends on what sort of approach that you want to take for this section for this week. You can attempt to sort of understand the theory, or template how you do a solution, and be able to do the two important tasks. The first one is to find the neutral axis, and the second one is to find the second moment of area. So if you want to understand the theory, in fact there's not really that much detail here in the notes for you to go through that, so you might have to find additional reading material. But the section starts off with talking about the concept of neutral axis, which is basically referring to the centroid of a beam as I'm looking down the side of it. So we're working out where that centroid position is. Now the principle is that if I imagine I'm bending that beam in a kind of just a very straightforward kind of way. So this is a bit exaggerated, so this doesn't look like this argument is valid. But you've got to imagine that this point here has been shifted inwards a bit, and so this line that's going through the neutral axis is not exactly the same as the centroid, but in principle it works out to be the same. It's referring to the point where this length, as it's going in, is going to be the same as this length. Now, because this deflection is exaggerated, this doesn't look like it's possible. It looks like that this length is going to be longer than that. But that's the argument. We've actually got a very, very shallow deflection, and the endpoints slightly move in, so the overall length of that line is going to be the same as that line, and that's what the definition for where a neutral axis is. What we're going to have on the bottom is that things are going to be slightly stretched, and then what's going to happen on the top, things are going to be slightly compressed. So you can go through and you can start deriving what's called the engineer's bending equations. So that derives the first bit to the equation. So if you want, you can try and understand that derivation, or you can just kind of skip ahead and then use the engineer's bending equation out of the box. The second bit is finalizing that engineer's bending equation. I would be tempted myself to kind of skip ahead to the work solutions, and then if you're interested, come back to the theory and derive them and see how it works. Most students tend to just really want to be able to use the equations and the techniques out of the box, so that would be my advice. But this is the second bit, and down here is the important one. So this thing here, and you'll find it in your formula sheet, it's called the engineer's bending equations. So that those first couple of pages is deriving that, and as I said, the derivation is probably not as detailed as you'd like. You probably want to refer to a different textbook to go for the derivation. And then a little bit explaining what these terms are. Okay, so this is a bit irrelevant really, but that's the important thing. And again, this is this is good to know because this is like structural analysis. Use this term, this sectional modulus term, but you're not going to see it appear anywhere else. As I said, the important thing is for you to be au fait with that equation there. So section modulus, don't worry about that too much. Now I worry about this, so this is important. So how do you go about finding the neutral axis, i.e. the centroid of the area? Now you've done this on your primal week, so a lot of you should find this straightforward. You've already done it. Okay. A lot of you might have come across finding the centroids in your previous A-levels at school for whatever reason. So this bit here should be kind of straightforward. I would strongly suggest that you follow the Yui notation for their approach to finding the centroid, because it builds on to for when you want to calculate the second moment of area. So I will make a video for you for the work solution, and make sure you follow it, even though you think, why are you bothering with all this palaver to find the centroid? So it would be good to get in the habit of using the Yui approach, because it is going to make your life a little bit easier for when you come on to do the second order of area. And then in week 7 we'll be covering problem sheet 9 and 10. So the first part you might even want to skip this, might just do a couple so that you're doing it in the right format. But you should have come across these sort of things in your primer, so not too bothered about it. And then the next bit is talking about the second moment of area and how that's calculated. And again, we've got theory here, which you could feel free to skip. What we really want to do is be able to quote the final result for what second moment of area is, which is given as the okay, so this is the one that we're going to normally use, because we're normally going to align, so ignore this, we're normally going to align the width, so the width is such that the depth, as it were, is the longer length. You're going to line up your post so that load is coming down onto the post there. The depth will be the longer length and the width will be the shorter length. So if you had beams, you obviously align them such that the thicker length is aligned against the load that's compressing it or trying to bend it. And when you do that, you find the second moment of area using this formula here. So the breadth B times by d to the power of 3. And this is a reflection of how stiff it is for when I try to bend it, and by pushing a load down on my beam in this direction. You got to imagine this is a long beam and I'm looking at the end section here, which kind of makes sense. So if I made that beam twice as deep, as it were, you could imagine, well, it becomes an awful lot stiffer. However, if I just make my beam twice the width, well, it is going to be more stiffer, but it's actually going to be stiffer in a linear sense. So we've probably experienced that in real life. So you might want to skip the derivation and then feel free, okay, this is the formula I'm going to use for working out the second moment of area. And I think there might be an example here from Arnold. Talk about different types of beams we're going to use. We're basically going to be using the rectangle beam. So even if we get something like a channel beam or an I-beam or a T-beam or whatever, we will break this down and make it into one of these. Now the other thing is that we could have a problem where we're just going to deal with a circular beam, so we're going to throw those formulas in. Be careful here, because the second moment of area is pi divided by 64, and d, big D, is referring to the outer diameter, and little d is referring to the inner diameter. And you will notice that this is called the second moment of area. You will find that there's two formulas that look very similar to one another. One's called the second moment of area, which is this one here, and then further at the bottom of the page is something called the polar second moment of area, and that's all to do with twisting things. And since we're not twisting things at the moment, we're bending things. This is the formula that we want to be using. There's no derivation of the parallel axis theorem. I could certainly explain it to you, but again, I don't think it's worthwhile. And parallel axis theorem is telling us how we're going to modify our second moment of area if we displace the beam a certain distance away from its natural neutral axis. So this is where you really want to now be following the template, and it's good to carry on from what you was doing before. So this explains the template. You can treat it like accountancy. and how you would start going from your initial table where you're finding the centroid, and then moving on to adding onto the table and then finding the second motive area. Notice that includes these H terms, which is the distance from the centroid to a particular located beam, the center of a particular located beam, where I'm going to treat each beam as a rectangle. And so that means each beam will have its own second motive area, and it also have this bit we add on, which I'll talk about later, the parallel axis theorem bit. So there'll be examples. Hopefully some of these will be up on the blackboard. Oops, didn't want to zoom in. And then I will do the work solution here for work solution 10. Okay. So probably for week 7, what we really want to be doing is knocking off maybe one centroid example and getting problem sheet 10 done. So you're in practice mode for your exam. Notice that there is another technique that you could use to find the second motive area. So one technique is to treat this problem here as if we've got 1, 2, 3, 4 rectangle beams all kind of glued together, or you could treat it as if you've got 2 where you've got a hole in the middle and then you take the void approach. So if you get onto that, all the way onto that, your tutor will explain to you that how to do that in further detail. That's it. I think. Let's just check. That's what I want done. Yeah, to page 123 for week 7.